In this section, we'll look at the approaches for managing system security. We'll start with looking at the factors that affect the system frequency response performance, and then we'll start looking at the operational levers that we can pull and the balancing act that entails to manage system security. And then we'll just look at a few case studies here and there of different approaches that have been taken all around the world. To illustrate the key factors affecting system frequency response, we're going to use an SFR model and perform sensitivities on the following base case. So here is the parameters of the base case. The first thing we're going to change is the system inertia. So the green line here is the base case, 15 gigawatt seconds. And if we increase the inertia, then we get a better RoCoF and a higher frequency nadir. Now, as we decrease the inertia, we get a faster RoCoF, or a higher RoCoF, and a lower frequency nadir. And the steady state or quasi-steady state settling frequency stays the same, pretty much in all cases. If we change the contingency size, so again, the green line here is the base case. So we increase the contingency size, we get worse response. If we decrease the contingency size, we get a better response. Similarly for load, the green line here is your base case. So if you increase the load to 3 gigawatts, then you get a better frequency response as you have more load damping effects, and vice versa as you decrease the load. Now that's making the assumption that there is load damping and the load damping factor stays the same as you increase and decrease the load. Now similarly for the load relief factor, the load damping factor, then if you increase the damping factor, then you get better frequency response, and vice versa if you decrease the load relief factor. We start changing the PFR. We changed the PFR quantity from 85% of the contingency size, and now we started dropping it to 60 to 70% and 60% of the contingency size. Then the frequency performance gets worse, and vice versa if we increase the PFR quantity. And lastly, the PFR speed of response, so the factor tau, has a similar effect in some ways to inertia. So the faster the response, the better the frequency performance, and the slower the response, the worse the frequency performance. To summarize the main factors affecting system frequency response, so this is ceteris paribus, so all things being equal, we'll look at each of the factors and what is needed from each factor to get a better frequency response. So a higher frequency nadir, a lower RoCoF, and a higher QSSF. So if you had a higher frequency nadir, this would go up. If a lower RoCoF, this would be less steep, and a higher QSSF, this would be also higher. So in terms of system inertia, you just need higher inertia to get a better nadir and a better RoCoF, but really there's no effect on the QSSF. And in terms of system load and load relief, they really come hand in hand, so I've just grouped them together. This higher load and higher load relief will give you better frequency performance all around. And same goes for the contingency size. A smaller contingency just can generally give you better frequency performance. In terms of the PFR quantity, a higher PFR will give you a higher frequency nadir, but doesn't really do a great deal in terms of the RoCoF, unless you couple it with a very fast PFR response. So that really ties in with the speed of response part of it. And you just need a higher PFR to get a better or a higher QSSF. In terms of the speed of response, for a better nadir and a better RoCoF, you just need a fast PFR, and it has no effect, like system inertia, on the QSSF. So some interesting points to note. So in many ways, all these factors are actually interrelated. So low system loads will tend to give you low system inertia, but also you probably have lower contingency sizes as well, as all the machines are running a bit lower. And it's all important to stress, I mean, we talked about this tutorial as a low inertia operation, but system inertia by itself is not really the most critical factor. There are actually multiple levers that can be pulled to maintain system security. We've talked a bit about the factors that affect the system frequency response. But the question is, why does it all matter? What happens if we just don't manage the frequency performance very well? Now, if you had a lower frequency nadir, then this leads to increased system security risks after a contingency. So, first risk is really the risk of under frequency load shedding, UFLs. So this is something that happened in the Swiss in January after a multiple contingency. And the a further risk is the risk of a system black event, so frequency collapse, and this is something that happened in South Australia in 2016. If we had higher RoCoFs, then the first sort of implication is the risk of sympathetic generation tripping on RoCoF-based anti-islanding protection. This includes rooftop PV inverters, and something we're seeing more and more of as well, where rooftop PV inverters, especially the old ones, are tripping off on anti-islanding or on other voltage issues. And higher RoCoFs can also increase the risk of just RoCoF protection relays on generators, for example. And then at really high RoCoFs, then we're at risk of generator pole slipping. So this is 1.5 to 2 hertz per second, which is quite fast. And there's a risk at very, very high RoCoFs that the UFL scheme doesn't work properly. That means the frequency is declining so fast that you're going through stages before they're tripping. And this could ultimately lead to frequency collapse. Here we start talking about the operational levers that we can pull for managing system security. So for each factor affecting the system frequency response, the following levers are possible. They're not just limited to this table, but here are just a selection of the things that can be done. So for example, for system inertia, we want to increase the system inertia. That's the lever, and these are the possible mechanisms by which we can operationally increase system inertia. So we could impose RoCoF limits or inertia floor limits. We could have must-run synchronous unit constraints, or we can have synthetic or virtual inertia services, or special inertia services such as synchronous condensers to be dispatched. Or finally, we can do out-of-market interventions, so dispatching out of merit. We could just turn on synchronous plant out of merit. In terms of system load and load relief, it's hard to really increase load relief operationally, but we can always just try and increase system load. So we can try and invoke some demand flexibility services. We'll talk a little bit about some of those later on. And in terms of the contingency size, we want to decrease the contingency size. So we could possibly invoke contingency size constraints or start doing out-of-market interventions, so reducing the largest contingency out of merit. And in terms of the PFR, we can increase the PFR reserves as an operational level, and to do so, we can try to have a dynamic PFR constraint that's based on system conditions. So it looks at the load, looks at the inertia, looks at the contingency size. Or alternatively, we can have mandatory PFR requirements. So we can ask all generators, synchronous generators in the system to have their droop control enabled. And in terms of PFR speed of response, we want to increase the speed of response if possible. And that means we can use fast frequency response services as a possible mechanism, or we can use fast load resources, so those that are tripped on under frequency relays. And also we can just decrease the deadbands on PFR response. A key point to highlight again is that managing system security is a multi-dimensional problem that involves balancing a whole series of trade-offs. So we have all these different operational levers to pull. So we could increase inertia, but we could also lower the contingency size, or we could raise the amount of PFR reserves that we carry, or we could increase the PFR speed of response. Now all these things are possible, but what is the sort of best or the optimal approach for each one? Now one way that we can visualize some of these trade-offs is through the use of frequency response security maps. So this is a conceptual diagram of the security map. So there's a 2D diagram, and here we have inertia on the x-axis and PFR requirement on the y-axis. So if you're in this area, we're secure. Now, when you have very high inertia, you need low PFR in order to be secure. Whereas as your inertia decreases, you need a greater amount of PFR quantity to stay secure. Now, taking contingency size into account, we get a 3D security map. And again, you have the same sort of general structure, but as your contingency size goes down, the amount of PFR also goes down. So this is something of a multi-dimensional optimization problem that you could decide which approach is the most optimal. Now we'll start going through some of the potential operational mechanisms for managing system security. The first one is the RoCoF limits and inertia floor constraints. So to begin with, an increasing number of jurisdictions are imposing more stringent RoCoF withstand requirements for generators. And you can see this on the table here for Australia, Great Britain, and Ireland. And you can see that the generators are expected to stay connected or withstand higher and higher RoCoFs. Now, RoCoF, as we've seen, is actually connected to inertia. So if you actually had RoCoF limits in the system, then we could actually translate that into an inertia floor constraint using the swing equation. So basically, we could say that the system inertia needs to be bigger than this equation, where you have a maximum credible contingency size and the RoCoF limit. Alternatively, this RoCoF limit can be framed as a contingency size constraint. So rather than saying what is the minimum inertia floor, we can say, well, what is the maximum contingency size that the system can handle given a system inertia? So these are examples of some jurisdictions with inertia floors. So the Australian NEM has an inertia floors for that's variable by state depending on how big they are when they island off. ERCOT has a critical inertia level, and Air Grid, Great Britain, and Nordic system also have inertia floors. Here we talk about dynamic PFR reserve requirements that are based on different system conditions. And here's a case study from ERCOT. So prior to 2015, ERCOT carried a constant 2,800 megawatts of PFR reserve at all times. But just recently, this is being changed to be a more dynamic requirement based on the system inertia. The PFR reserve requirements were calculated via offline studies, and the reserve requirement follows a familiar exponential relationship with respect to inertia, as you can see here from the diagram. So when you have more inertia, you just need less PFR. One thing they also did was they actually included an equivalency ratio for load resource PFR, which are triply under frequency relays, and they're very fast. So they can really consider, fast frequency response, vis-a-vis the normal generation PFR. And so what you're saying here is that if you were sitting at 200 gigawatt seconds of inertia, then 1 megawatt of load resource PFR is actually worth 1.535 megawatts of generation PFR. So in this way, then you're sort of incentivizing more load resources to come in at lower inertia levels than at higher inertia levels. Mandatory PFR requirements. For a number of years, the Australian NEM saw a real degradation in frequency control performance. So this is what the frequency histogram looked like in 2005. You can see it was really nicely centered around 50 hertz. And by 2018, it really degraded so that it was just flopping around between 50.15 here and 49.85 hertz. And this was really largely driven by synchronous generators sort of detuning or disabling their speed droop controls and or widening their deadbands. So they were just really not very responsive to frequency deviations unless they were participating in the frequency control ancillary services market. So they were actually getting paid to do it. And this was partly to do with avoiding disincentives associated with being responsive to a frequency. So yeah, dispatch target non-compliances. So in June 2020, these rules were changed to require mandatory PFR for scheduled and semi-scheduled generators with a small deadband around 50 Hertz. And mandatory PFR requirements are also in effect in quite a few jurisdictions around the world. So Brazil, Great Britain, Ireland, Singapore, Spain, the US through a FERC order, and also in the Swiss. Now, mandatory PFR means that from a frequency control in large disturbance point of view, is that you've got other responsive plant that will respond to a large disturbance event when the frequency declines. So that means that you have a little bit more fat, basically, if you have a large contingency. Then if you didn't have any responsive plant, then you really are relying purely on your PFR that you have contracted or bought from the market. A fast frequency response, FFR, as the name suggests, is PFR that's delivered very quickly. And as we saw in the factors affecting frequency response, it can improve the frequency nadir and the RoCoF. So FFR can be provided by a variety of generation sources, but it is typically activated by fast-acting control systems. And it's based really on measurement of local frequency and may include one or a combination of the following methods. So a proportional response is an injection of active power that's proportional to the measured frequency deviation, so like a droop response. A step response, so a fixed amount of active power is injected into the system once a frequency or a RoCoF trigger has breached a preset threshold. And a derivative response is where the injection of active power is actually proportional to the RoCoF or the measured RoCoF. It's like inertia type emulation. So note that the load responses and inertial responses are sometimes referred to as FFR, but these responses are treated separately in this discussion. Here are some examples of different types of FFR responses. So for a decrease in frequency, you have a proportional inertia-based FFR, and then a stepped-based FFR, and you have a proportional FFR from a battery energy storage system, and a stepped one. The specification and assessment and the certification of FFR, probably the following parameters should be considered. The type of response that will be provided, so a proportional, step or derivative response, the magnitude of the response, the activation delay, a response time, the sustaining time, so this is how long the response can be provided, and the availability of the response, so unavailable operating conditions. It's also important to note that FFR is not actually equivalent to inertia. FFR is not an intrinsic response, but it's a control response. So you need a control system to create the FFR response, and requiring the measurement of frequency and or calculation of the RoCoF and some logic to deliver that response with some inherent activation delay. And one of the main problems is that FFR can actually fail. So you might have a control system failure, or it can actually activate incorrectly due to some measurement of control logic error. By way of example for an FFR is a Hornsdale Power Reserve, which is a battery energy storage system located in South Australia. It's 100 megawatts, 129 megawatt hour lithium-ion Tesla battery storage, and it's co-located with a 316 megawatt Hornsdale wind farm. It's currently a 50 megawatt, 64.5 megawatt hour expansion that is currently under construction. Hornsdale participates regularly in the NEM FCAS markets, frequency control ancillary services, and here's one example of how fast frequency response really helped in an event that occurred in South Australia. So this event occurred on the 25th of August in 2018. We actually talked about this event before, and it was actually the separation event between New South Wales and Queensland that then later on turned into a separation event for Victoria and South Australia. And in that event, the frequency dropped to 49.2 hertz, and the Hornsdale Power Reserve actually provided a proportional FFR power injection, and provided quite a lot very quickly as well. So it went from absorbing 38 megawatts to injecting 10 megawatts within the first second. And then as frequency kept on falling, it injected another 40 megawatts in the next 3 or 4 seconds before then declining and backing off proportionally as frequency recovered. So that's a really good example of fast frequency response where normal generators would not be able to respond basically 80 odd megawatts within the first 4 or 5 seconds. So not many generators can do that, and this is one of the sort of real advantages of battery energy storage is to provide FFR. Synthetic inertia is a term that's bandied around quite often, mainly for wind turbine generators that have their converter controls configured to mimic the inertial response of synchronous machines and provide some kind of synthetic inertia. It's also referred to as virtual, emulated, or artificial inertia. But in many ways, this kind of synthetic inertia, which is still control system driven, is actually not real synthetic inertia, because for an inverter to really provide synthetic inertia that is really equivalent to normal inertia, it really needs to act like a voltage source and form its own voltage reference. So in other words, it needs to be grid forming as opposed to grid following. And quite a lot of the wind turbines that call themselves synthetic inertia are actually grid following and act more like fast frequency response than they do to true inertia. So there are inverters that can be configured like a grid forming inverter and then configured to act like a classical synchronous machine. And these are something like the Tesla or the ABB virtual synchronous machine, and an Israeli company called Synvertech has this thing called a synchroverter. And so the basis for the inverter controller is essentially this classical synchronous machine model. And the way it works is that the inverter itself has a voltage reference. So it creates both a voltage and an angle. And when then there is a frequency disturbance in the system, it causes the grid voltage phase angle to change. And so when that changes, what we'll find is that the active power going into the grid also changes through equation 1, because this is at the moment fixed, and then this value here is changing due to the grid disturbance. And so the inverter automatically injects more active power into the grid. And that's really the inertial response. And so that change in PE then actually causes a change in the frequency of the inverter. This then causes a change in the voltage phase angle of the inverter, so the rotor angle, so-called. And this change then causes PE to change again, and you repeat this loop until a new steady state is reached. So that's really in a grid forming sort of capabilities of an inverter. However, really for that to really work, you really need some kind of active power source to actually supply that energy when the power changes occur in the system. An example of synthetic inertia in Australia is the Dell battery energy storage system, which is also located in South Australia. So a much smaller system, so 30 megs and 8 megawatt hours, so much smaller than the Hornsdale Power Reserve, but it really was designed to provide ancillary services and provide grid stability and reliably in this one area called the York Peninsula. So the inverters themselves were actually manufactured by ABB using their power store product, and it has grid forming capabilities and virtual synchronous machine functionality, synthetic inertia functionality. And so the block diagram here sort of explains roughly how it's put together. So you have a frequency governor, which is sort of more like the fast frequency response component, then an inertia block, which from here you can see looks a lot like the swing equation. And then you've got some of the voltage control loops, and then you've got the inverter itself going out into the grid. This is an example of the Dell battery in action. So there's another South Australian separation event, this time on 16th November 2019, when the 500 kV Haywood interconnector tripped after a fault. And in this case, we had a large frequency spike because South Australia was exporting energy across the interconnector at the time. And so as soon as the spike happened, you can see that the BESS at the time was discharging, and you see an immediate inertial response, very similar to what you see from a synchronous machine, and then you'll see a fast sort of frequency response ramping down basically towards 0 megawatts. So this sort of demonstrates both the inertial or synthetic inertia capabilities of the BESS as well as the FFR capabilities. As mentioned previously, end-use load resources can be used as primary frequency response by adjusting their demand or by tripping off completely during frequency changes. Hence, distinct from under-frequency load shedding, which is unintentional and it's more like a protection scheme, these load resources are tripped intentionally and are typically compensated for providing this PFR, either through a contractual mechanism or through a market-based system. There are two types of load resources that can be used as PFR. The first one is through load tripping, where the load is just tripped off based on under frequency or RoCoF relay thresholds, and this really can only be used for under frequency events or like a generation contingency. And these load resources provide very fast and reliable PFR. Usually larger industrial or commercial loads are used in load tripping schemes like smelter potlines. And smaller loads can also participate via aggregators, such as NLX. The second type of loads is the controllable loads. And these loads respond to frequency changes by a control change in demand. And so this is probably a bit slower than load tripping, depending on how the control scheme is set up, but it was a process control scheme or sort of some control logic to adjust. So for example, motor set points, VSD set points, etc. So examples include the control of water heaters and HVAC, and also more recently the power management of data centers. Here's an example of an aluminium smelter in West Iceland that is fitted out with a dynamic load control scheme. And you can see in this event, it was actually a over-frequency event, and you can see that as the frequency went up, the active power also went up. And you can see it's not particularly fast. I mean, we're talking here in the time scales of 10, 20, 30 seconds, so it takes some time for the control scheme to operate. And as the frequency goes down, the load also goes down. A couple of years ago, Hydra Quebec ran a very interesting trial to use distributed load resources as PFR. So in this trial, they used residential water heaters and they retrofitted them with a local controller here to measure frequency and provide a proportional fast frequency response as opposed to on-off, activating within 250 milliseconds of a frequency disturbance below 59.8 Hz. So the control strategy was that whenever there was a a drop in frequency, in the initial stages, it would modulate the load with a linear droop of 1% between 59.8 and 59.2 Hertz. And then it would modulate for 15 minutes on droop, and then eventually, after 15 minutes, it would progressively return back to normal operation. I'm not entirely sure where this trial has ended up. I believe there was quite a successful trial, and they got quite some good results with it, but I'm not sure how much widespread adoption it has had after the trial. Demand flexibility services. These refer to the time shifting of discretionary electricity consumption to better align with system conditions. So in this case, we were talking about the preemptive increasing of load when there is high output from variable renewable energy generation. And for the context of the managing system security, in this case, what we want to do is increase the load so that we get more load relief, if possible. So a couple types of discretionary loads that have been identified for flexible schemes. They include electric water heating, electric vehicle charging, space heating, and cooling, so ice storage or commercial air conditioning. There have been quite a few trials in the works around the US, so smart vehicle charging trial, ice bear storage, grid interactive water heaters, so actually quite similar to the one in the Hydra Quebec trial. So the smart thermostat trials or electric thermal storage trials. But I guess for managing system security, it would be desirable to bring on loads that provided load relief, so motor-driven loads, such as compressors. I mean, electric water heating and space heating probably wouldn't really help that much in terms of providing that load relief. An emerging risk to system security that we're seeing at AEMO in recent years is the widespread tripping of DER after system disturbances, such as network faults. And this is really a risk that is emerging in systems with lots of penetration of rooftop PV, such as parts of the NEM and the Swiss. And the tripping of DER along with another contingency can really lead to very large contingency sizes, especially during clear sky daytime hours. And here's a case study again of the Queensland and South Australia separation event from 2018. So a lightning strike hit the QNI interconnector up near Queensland, and it triggered a series of faults that led to about 415 megawatts of rooftop PV inverters tripping. And here we put here some zones, zone 1, zone 2, zone 3, which are like distances away from the fault location. And this graph shows how much was tripped at each zone. And very close to the fault location, you'd expect the voltage to be quite large, and sure enough, there's quite a lot that tripped off. But as you went further and further away, we're still seeing PV inverters that trip. You have here 90 megawatts in Victoria and 60 megawatts in South Australia, and they're states that quite far away from the fault location. So the majority of the PV inverters that were actually not electrically or geographically close to the fault location, so zones 2 and 3 on the map, you can see here in the blue, the majority here were actually pre-2015. So they were designed to the 2005 standard of the inverter requirements standard, AS4777, and which was actually revised in 2015. So they were actually probably non-compliant to the new standard and some of the ride-through requirements in the new standard. So you would like to think, or hope anyway, that as these older inverters get replaced, that the new inverters are able to ride through these kinds of events. The bench testing that was done by UNSW indicate that depending on the state, up to 20 to 40% of inverters will not ride through some deep voltage sag. So they're probably the ones that were experienced in zone 1, so very close to a fault location. So between 8 and 33% will not ride through a 30-degree voltage phase jump, and 4 to 32% will not ride through some very high RoCoFs here, 1 Hz per second.